6 Abbott Road in Lexington. So there will be a bus leaving from the Center for Astrophysics, and Bill Nehring, if you want to attend it and you need information, just contact Bill and he will let you know where to meet the bus. I think it's at around 11:15, is it?
That's right, 11:15, that's correct.
Yeah, leaving from 60 Garden Street, which is up on Garden Street. Which parking lot is it leaving from?
In the parking lot near Bond Street.
The Bond Street.
Mm-hmm.
Okay. So you're most welcome. You will meet a lot of other postdocs and people from other departments if you come along, and the food is great usually every year.
No, Avi makes it all.
No. That's why it's good, because I'm not making it. We do plan weekly events in addition to the colloquium that we have today, every Tuesday. We want to have on Monday or some other day a philosophy forum. We had that last year, and Faraz will organize that and coordinate it. We'll announce it as soon as you fix the time, and it will be about the philosophy of black holes. People gather together in this room and discuss it. And also Ramesh Narayan's group meeting takes place at 1 p.m. on Mondays, and the Event Horizon Telescope used to have a meeting once a week for everyone, right?
We have hackathons.
When is that?
Well, they're being reorganized right now.
Okay, so it's not set,
I
right?
thought Wednesdays are.
Well, we have group meetings on Wednesdays at 2:00.
Okay, group meetings.
Yeah,
or
they should
technical.
send me a note if they want to participate.
Michael Johnson is organizing it. All the events will be posted also on the website. We have a calendar, so, and you can sign to the Google Calendar of the BHI so that it will appear automatically. The other thing that came about this year is a new PhD consortium, which is a PhD program that allows students from any department, there being astronomy, physics, math, history of science, or philosophy, that are interested in black holes to take courses from all these departments. So they don't need to, they are admitted to a particular home department, but they can take courses in all other departments as part of a thesis related to black holes. So that's a new thing at Harvard, and the graduate school approved it in the spring. And so starting this year, any graduate student that wants to pursue a PhD in black hole physics, or black hole philosophy, or black hole mathematics, and wants to do it in an interdisciplinary fashion, is able to do so. And that's great. And we already have 2 students signed up for this program. It just started. As of today, we have 2. So. The first is Tiffany. I don't know. Oh, she's not here, I guess. She's from the history of science. And the second is Delilah Gates. Also is not here. Oh, she's here. Here she is, working with me. The last thing I wanted to mention is the fact that, I mean, we'll hear today about LIGO, but there are rumors that LIGO discovered over the summer very important events, and not just one, and not just 2. But one of them is particularly, and I'm just repeating things that appeared in the press. I'm not revealing any secrets, even though...
You didn't hear them from me anyway.
Yeah, exactly. Well, the strange thing is I sent an email about one of the reports in Nature about the results, and then I got emails back from LIGO people, or people that work with LIGO, saying no comment. I didn't ask for their comment, but that implies that there must be a lot of truth to what was reported. Otherwise, they would immediately made some comments. And the comments that the report in Nature was that at least one of the events has to do with 2 neutron stars smashing at a distance of 40 megaparsecs, and followed the gravitational-wave detection was followed by electromagnetic counterpart. And when you say electromagnetic, it spans a wide range of frequencies. So shortly after again, according to that article, shortly after the detection of gravitational waves, or around the same time, there was already an indication for an electromagnetic counterpart. The localization was very good, so telescopes could point in that direction. They found something at the right distance. That's the amazing thing, that you go to the right place on the sky and find, from gravitational waves you can infer the redshift or the distance, and the same can be immediately done if you find a galaxy where there is a transient and they match. So that's quite remarkable. The reason it's important is because electromagnetism allows us to get much more information about the source and the nature of the source. So this opens a whole new field. This could be a subject for a second Nobel Prize. Hopefully the first one will be given this year to LIGO. So anyway, without further ado, let me allow Michael to introduce the first speaker.
Great. Well, yeah, I'm really delighted to introduce Nergis Mavalvala to kick off our Colloquium series for the year. So Nergis is a longtime member of LIGO collaboration, going back to her days in graduate school at MIT, and she's now the Curtis and Kathleen Marble Professor of Astrophysics at MIT. So she's won many awards, including being named a MacArthur Fellow and recently being inducted into the National Academy of Sciences. And today she'll tell us about future directions in gravitational wave detection.
So thank you, Michael, and thank you, Avi, and hi to everybody and all my friends in the room. So let me just say a little bit about my talk. I could talk for hours and hours. Luckily for you, I'm not going to. I had to choose what could I tell you about. So I could tell you about LIGO discoveries, but you've probably heard about that, and that would take all of my talk. I could tell you about how the LIGO instruments work, but that would take much more than my talk. I could tell you about how we make improvements to the instruments. That would take up many talks. So I decided to do it all. Okay? So here we go. Prepare yourselves for a ride. And this is really, you can think of this as a story. And occasionally we'll do some science you may not have come across. And that's just an opportunity for you to think about things you've never maybe spent any time thinking about. So I'm going to speak about gravitational detectors and where we're going into the future. And I'll just say up front that anytime I show you LIGO or LIGO-related data, as you all know, this is a big collaboration, so I'm just the messenger. And then I'll show you some data from my own group, but my group is also big, so I'm just the messenger. So everybody has seen pictures like this, where this is the full compendium of LIGO discoveries that we know of, and that is to say we have black hole mass over here, and over here we see what was known about black holes by studying X-ray emission of accretion around black holes, and this is what we thought the masses of these stellar mass black holes should be. And then this is the population that LIGO has begun to measure, and this is done from its largely from its first observing run and one from its second observing run. And I'll just say LIGO is operated in periods of 6 months of observation and then typically a year of downtime to make improvements to the instrument. And what you should take away from this is, in a very pictorial way, that we think these black hole mergers that we're observing are opening up a population of stellar mass black holes that we haven't known about before. So what I want to do is I want to tell you a little bit about what are the instruments and the motivations behind these instruments that take us there. So the first thing you can ask is for these first 3 observations that were done in the first observing run of LIGO, this is the best we could do for localizing them on the sky. And this was done with the 2 LIGO detectors in Washington State called H1 and in Louisiana called L1. And we asked ourselves the question of what would these have looked like if Virgo, the Italian French detector in Italy, had been on the air during these observations. And you can see that the localization can get quite a bit better. And in particular, if you notice this one, which was the original, by the way, the first one, still one of the highest signal-to-noise ratio guys, and it's located in a place in the sky where LIGO and Virgo have good sensitivity. It could have really narrowed down where these sources are. So that has motivated, of course, a big push to get many more such observatories running with large baseline across the planet, so you can, by triangulation, get a better localization of in the sky of objects, and that sort of motivates this whole panoply of detectors. So the 2 LIGO detectors in Louisiana and Washington have been operating in this phase, the second phase, we call them second generation detectors, since 2015. Virgo, as you'll see in a minute, has been a few months behind, and now in the very end of our second observing run and in August this year, joined observing run 2. And then there's then LIGO is 4 kilometers long. These are long detectors. Virgo is 3 kilometers long. And then the next detector that's sort of in the offing is the Kagura detector in Japan, 3 kilometer long detector that should be running in the next few years. There's also a smaller 600-meter detector called Geode in Germany that kind of, because it's so much smaller, it doesn't have the sensitivity to compete with the big guys anymore, but has been an important part of the network. And then there's LIGO India, which is essentially a LIGO detector that is being placed at a site in India. And then the Space Observatory, LISA. Now LISA, I'll just point out, is completely complementary to these terrestrial detectors because LISA works in a different frequency band. And therefore, you cannot think of LISA as adding to this network. You have to think of LISA as really expanding the frequencies over which we can make gravitational wave detectors. You can think of LISA as the radio telescope analog of optical telescopes, which are the terrestrial ones. Okay?
So Kagura and Virgo, how are the insensitivity relative to LIGO?
I show in just a moment. What can you do when you have many more detectors? So here is what kind of sky localization you could do if you had the 2 LIGO detectors and Virgo. And you can see some patches in the sky you can locate very well because the sources are quite well oriented in those places. And there are other parts of the sky where you have very poor, like hundreds of square degrees error boxes. And then we asked the question of what would happen to this network if you could add a detector in India, and that's what happens. You can see that you get much better localization across most of the sky, and then this motivated the National Science Foundation and their counterparts in India to come up with a plan to install one of the US LIGO detectors in India. So let me just say a little bit about where we are at with LIGO and all these counterparts. And this is a detail. So here's what we do with LIGO. So if you just think about, you'll see plots like these all the time describing how well we think our detectors are working. They have frequency on this axis, and you notice the frequency is audio band. So this is the first thing you should remember is gravitational waves that these terrestrial detectors detect are in the human audio band. On the vertical axis is just our sensitivity to gravitational wave strain, and these funny units of per square root of bandwidth. If you don't like those units, you simply take the bandwidth of the detector and you multiply by its square root to get you some RMS strain. Important thing is that the first phase of LIGO that ran from 2000 to 2010 is the green curve. Advanced LIGO during observing run 1 was the red curve. The blue curve is what we have designed advanced LIGO to be, which is a design that we expect to achieve sometime in the 2020 timeframe. And already we are thinking about what kinds of upgrades can we do to advanced LIGO to get the cyan curve. And my talk is going to sort of cover a little bit about what are the things we have to think about to achieve these curves. Okay. Now I won't say a great deal about what these curves are. This is a very interesting set of curves because this is actually a paper that was written in 2013 where scientists tried to ask the question, what do we think advanced LIGO and advanced Virgo will be doing in these different time frames? And the bands simply show that there's uncertainty in how the instruments would perform. One of the things that I do like to point out is that at least with regard to advanced LIGO, in 2015, so 2 or 3 years earlier, we wrote down that in 2015 we think we should be observing with a range of 40 to 80 megahertz. Now, what does this range mean, by the way? Do people know how LIGO tends to talk about these range? This range is simply asking the question: if I have a garden variety pair of neutron stars that go through coalescence, what's the distance to which I could see those? Okay, that's the question being asked with an SNR of 8 and with random average orientation. So that's the question being asked, and so that's how we write it in megaparsecs. And so both observing run 1, which was 2015, and observing run 2 that just finished last week, have kind of followed the blue and the green curve. So we like to say that we are on schedule with what we thought we'd be. You can also turn it around. Maybe we are only on schedule because we drew these curves, and maybe something different would have made us act differently. I don't think so. This is the best we can do with the instrument. Virgo has been delayed a little, and I'll say a little bit about that, but they too have made some predictions for what they think their sensitivity would be. And you asked the question of sensitivity. So you can see Virgo always knew they'd be a little bit later. But if you look at these sensitivity curves, they're quite similar, the LIGO and Virgo curves. So these two detectors are kind of both close in time and in sensitivity goals. Now Virgo itself actually came on the air in November 2016. They had some setbacks of details I won't talk about, but this is an interesting curve right here. So the most important thing to carry away from this slide is the last thing. In August 2017, so a little over a month ago, Virgo joined Observing Run 2 with advanced LIGO's 2 detectors. So we now have a 3-detector network. And we had it for about a month because Observing Run 2 ended at the end of August. So for 1 month, there were joint observations with Virgo. Now you can see Virgo's sensitivity is quite a little bit different, 20 megaparsecs compared to the over 100 that LIGO has been doing. But a good duty factor, its uptime is good, and these are the curves that you might find interesting. The most sensitive is the blue guy, which is LIGO Louisiana. The red guy is LIGO Washington, which has had some troubles during O2, so not quite as sensitive. And then Virgo is purple, and then Geo, the little German guy, is the black curve. But you can see that this Geo cannot really compete because all your at the places where you're most sensitive, which for us is typically in sort of the 50 to 150 hertz band, Geo is just not a player. Okay, so this is the region which sort of defines that number that we quote of how many megaparsecs you can reach out to. Okay, Kagra is an interesting beast, and I'll call it a beast because it's quite difficult to do. So the Japanese have made 2 interesting decisions for their 3-kilometer detector. The first was to put it underground. So the Japanese detector actually is in the Kamioka mine, the same place where Super K is. And the other decision that they made was very early on is to have, right from the start, a cryogenically operating mirror. So one of the things that really bothers our measurement is the thermally driven vibrations of the mirrors of LIGO. So the measurement that LIGO tries to do is we're trying to measure the motions of mirrors due to passing gravitational waves. Anytime you have any other motion, that's a pain that you have to remove. And so one of those motions that Kagra deals with is thermally driven motion, but cryogenic operation is a very difficult problem because anybody who's ever worked with cryogenics, and I'm not sure people who think about black holes have, but I'll put it out there anyway, is when there's 2 things you have to worry about a lot when you cool. The one is, can you get enough heat out of the system? But the second one is, does that cooling system put vibrations back into your measurement? So it's been a really hard problem, and LIGO has chosen not to go this path for at least another decade. Okay, so but given that Kagra is still making progress, they expect to have first observations in about 2018. Okay, so that's what you need to know about Kagra. Those will be modest. The first observations will be at modest sensitivity, with eventually probably in the 2022 timeframe to be up at like full steam. LIGO India is actually an interesting character. It's part US NSF and part India's Department of Atomic Energy, which turns out to be the equivalent of our National Science Foundation. And the only interesting and important thing that you should know about it is it's moving ahead, and with likely a projected date for joining the global network of about 2023. And for anybody who's followed LIGO India, the 2 most interesting things that have happened in the last couple of months is land acquisition. The first land package has been acquired. Now it turns out when you look at a map, you look at India and you say, boy, that's a big landmass there. But it turns out it's really dense. People are everywhere. So finding 4 kilometers in a linear L shape is really, really hard. And so this is a big achievement already. And so I think that's sort of moving along. So that's where we are with this global network of terrestrial detectors. So let me just say, where do I think this is going to go beyond the present time? So near term, you can see what's going to happen. We're going to have advanced LIGO plus upgrades. Remember I showed you the sine curve of upgrades we're already thinking of. We're going to have advanced Virgo with similar upgrades. And then Kagra and LIGO India will come up. So this is in the next 5, every time I say 5 years, but I've been saying it for the last 5 years. So, take give or take. Okay, so that's what we see coming in this generation of detectors. Then you can think about some mid-level upgrades, which we sometimes call the Voyager upgrade, which is sort of a factor of 4 improvement compared to advanced LIGO design. And finally, in the 20-year time frame, we are already thinking about what would be called new facilities. So, just like with optical telescopes, eventually you have to go to bigger glass. This is the same thing. Eventually you have to go to longer instruments. So the length is a knob you turn for gaining more sensitivity. It gives you the biggest bang for buck, if you will. So that's in the 2 designs, a European SCARY, a design called the Einstein telescope, the American SCARY design called Cosmic Explorer. But here's what you should think about. Here is the first phase of initial LIGO Virgo. This band here, about a factor of 10 better than those, was advanced Virgo, Kagra, advanced LIGO. Then there's this dash curve, which might be this mid-scale improvement, and then Einstein telescope or Cosmic Explorer are expected to be a full factor of 10 or more better than advanced LIGO. And these are typically called 3rd generation detectors. Now, you might ask, writing down curves is cheap and easy, but what's the technology that goes behind it? And that's really the question that we have to always keep our eyes on. And to answer that question, you have to know what makes advanced LIGO, what limits it. So, some people say, what makes it as bad as it is, because you're already thinking of the advanced instrument. I like to say what makes it as good as it is. But either way, you see 2 things that are really important. So you've seen these curves before, and this black curve is just the advanced LIGO design that I've shown before. There's 2 things that are very important. The first is this purple curve that actually makes up most of the black curve, because the black curve is the sum of all these noises. The purple curve is something we call quantum noise. And I'm going to talk a lot about that in the next couple of minutes, because it's both bizarre, interesting, fun, and fundamental. There's another noise source, this red line here, which we call coding Brownian noise. It's really the thermal noise, the thermally driven motion of the coatings, the optical coatings on the mirrors. And it turns out that those are are the 2 big limiting noise sources for advanced LIGO. And I want to say one thing that I like to point out on this curve, even though it doesn't have a lot of relevance to the rest of everything I want to talk about. You'll see a curve on here, this green curve, that calls itself gravity gradients. It's sometimes better known as Newtonian noise. What is this green curve? This green curve is to do with the fact that local G is not constant. Now, why is local G not constant? Well, you can imagine most simple-minded thing is you have one of these exquisitely sensitive mirrors of LIGO hanging, pointing down to local G, and being an inertial test particle. And up above it comes a cloud. Now, cloud has mass, and that mass is moving. It has such a fluctuating mass distribution. What does our mirror do? It responds to it. And because things like clouds and density waves in the earth, they move at relatively slow, long time periods or low frequencies, you can see this noise here. And if you ask why do you need to build LISA? Why can't you just take a terrestrial detector and make it a low frequency detector? This is the reason. If you want to get past this, you've got to get off the planet. That's real. So really, that's the motivation for anybody who says LISA's too expensive, do it on the Earth. The answer is that. The one simple stupid curve, but so painful. Okay? So that's really the 2 things. So I'm going to tell you that the thermal noise is a problem that other people are working on and very important to solve. I want to spend the next couple of minutes talking about the quantum noise, because that's the work that my group does, and it's I'm not biased or anything, but I think it's pretty fundamental. So let me just say what are the technologies that one must then come up with to do better than advanced LIGO. So for this Newtonian noise, or this noise that I told you about local G not pointing in the same direction or having time-varying fluctuations, you can instrument the whole system with seismic sensing arrays and try to subtract some of that. Or you can also go underground. Those noises you're shielded from them better underground. That's part of Kagra's decision to go underground, which brings up another host of problems, but that's one way to do it. For thermal noise, you can do cryogenic cooling. Again, that's something that Carver has chosen to do in its first step. Or you can use lower dissipation materials so that intrinsic thermal fluctuations are reduced. And then for the quantum noise, you have to use some exotic states of light. The quantum noise in our instruments comes from the standard quantization of light. So why do we call it quantum noise? It comes from the fact that light is quantized. We measure photons. So we'll come back to that. And then finally, I will say without hesitation that no matter which of these technologies you work on, eventually you have to go to longer arms because you've run out of all the things that you know how to do in 4-kilometer long facilities. Okay? So that's the idea. So third generation detectors has a whole set of options to consider for these. Almost all of them will consider longer arms, 10 to 40 kilometers. Almost all of them are looking at the question of underground versus not, cooling versus not, different kinds of materials with lower thermal noise versus not, different ways of designing your detector so you can have, for low frequency gravitational waves, you have one kind of detector, for high frequency, a different kind of detector. But there's one technology that every single one of these designs, no matter who's designing it, counts on, and that's called squeeze light injection. And that's because it's a technology that's somewhat mature compared to all these other ideas. So let me tell you a little bit about squeeze states of light and what they do for us. So quantum engineering is this little segue I'm going to do. And I really like to say the future is now, because these were ideas that we had invented for very future detectors. But I'll show you in the next minute and a half that this is actually going into advanced LIGO now. Even as we speak, our students from MIT are at the observatories installing one of these. So let's ask, where does quantum noise come from? So now I think, if you've been asleep until now, this is a good time to wake up, because this is now where the fun starts. So let me ask you some questions. So the first question is, imagine I have an interferometer like this, and I have a laser, and this is a theorist's interferometer. It's idealized. So it's a perfect beam splitter. Half the light goes this way, half the light goes that way. Perfect mirrors, they reflect the light right back. And now I have arranged this length and this length, so I have perfect destructive interference here. Now, perfect destructive interference means no light should come out here, it's destructive. So first question is, where's the light going? Because we still have to conserve energy or the number of photons. Where's the light going?
Back in the laser?
Back to the laser, exactly. Okay, now let me ask another question. Imagine I had noise on the laser, and I'm not going to make any judgment about whether it's classical noise or quantum noise. Lasers are noisy, and they have both kinds of noise. If I had noise on the laser, where is that noise going to go? Back to the laser. The noise and the coherent photons don't know that they're noise photons or coherent photons. They just see the geometry of the interferometer. And if the light goes back that way, so does the noise. Okay? So now we say quantum noise, and so this is the fluctuating number of photons, and typically a laser is a Poisson distributed source. So if you have n number of photons, or you have square root of n of noise, and that goes back to the laser. So if I make a measurement here, I should make a noise-free measurement. Does everyone agree? Yeah, so from everything I've told you so far, yes, you're right, it should be. But it turns out that I have left out one really important piece of a quantum optical system, or any quantum system. This just happens to be a quantum optical system, which is that in quantum mechanics, when you have an open quantum system, what happens? Does anybody, if you've studied field theory, you've come across this before. Yeah, someone is whispering the electromagnetic vacuum. So now see what happens in this interferometer. So everything I've told you so far is true. This is an idealized interferometer. All the light and the noise goes back there. But look at this open port. This port is blocked by a mirror. This port is blocked by a mirror. This port is blocked by a light source. This port is open. So what happens? The quantum vacuum goes in there. This is just a vacuum state. Notice that, by the way, this notation for quantum optics is simply x1 and x2. You can simply just think of as amplitude and phase of light. It's not quite true. Those are not the Hermitian operators. You have to reconstruct it. But you can see what this represents is that in the classical world, if you had no photons, you had zero, you would have a nice infinitely small dot at the origin of these axes. But in quantum mechanics, you have uncertainty. And you must have this quantum, and that's the 1/2 h bar omega quantum uncertainty of the vacuum state. This beam, light beam, you can think of it as just a set of vacuum photons, if you will. These photons go into this interferometer, and because of the symmetry of the beam splitter, just for the same reason the laser light came back to the laser, this light beam comes back to this port. Now what else comes out of this port? If you have a gravitational wave going by, this mirror moved a little out, this mirror moved a little in, and a little bit of real light comes out too. And it's the beat note of the actual light and the vacuum state that gives you the noise. So here's your little signal phaser. If this was a completely classical system, all I would see is that it is the tip of this arrow, perfectly well defined. But here now it has to superpose with the quantum vacuum state, and now I see a fluctuating signal. That's where the quantum noise comes from. So this is a very important thing to understand. It was highly debated in the 70s and until about 1980 whether it happened this way or not. And this debate was kind of settled by the work in Kip Thorne's group by, at the time, his graduate student Carl Caves. Now let me just say, what does this have to do with squeeze states? Now imagine I could, instead of having this ordinary vacuum state, imagine I could make a squeezed state. Now if you've never come across a squeeze state, it's very simple to think of geometrically. A squeeze state, let me just say what it is. A squeeze state looks like this. It's simply a state where you can make the noise along one axis smaller, but you must make the noise along the other axis bigger. Otherwise, you're violating Heisenberg. But here it's saying the product of the uncertainty is still h bar. And if you can arrange that in your experiment, then when you make a measurement at the output here, indeed what you'll see, your signal phaser stayed the same, but you cleverly orient your squeezing ellipse for the narrowest part to be along your signal, and you can make a better measurement. Now what's the price you pay? The price you pay is that you dare not measure even a little bit along this axis because you have much increased noise along that axis. And that we can do in the experiment. So here's an experiment where we did that. I won't go into the details of it. This was an experiment we did actually in 2011 in initial LIGO, where we have the whole interferometer set up exactly as it would be. This is the output, here comes the laser. And here where we would measure the gravitational wave signal, we wheeled up a squeeze light source, which is really just, you can think of as an entangled photon source. So at this output port, instead of ordinary vacuum, we forced there to be squeezed vacuum states. And then here was the result, where the red curve shows what LIGO at the time was doing without squeezing, and then the blue curve shows that any part of the spectrum where we were limited by quantum noise, you could do a little better. Okay? So that was the first proof of principle of this experiment, and since then we've done improvements. We only saw 25% improvement, but we have much better now, and we're now installing, I'm going to skip this part, we're now installing a squeeze light source where we're aiming for about a factor of square root of 2 improvement at the frequencies where advanced LIGO is sharp noise limited. Okay? So I just want to say this is a technology where you can think of as something that's ready for use. Now here is some toy curves that we've drawn about using technologies we think are achievable for Cosmic Explorer, which by the way is a 40-kilometer instrument. So here's what advanced LIGO is. Here is what we think we can do in improving any 4-kilometer instrument. Here, red curve is what we think that the Einstein telescope, which is a 10-kilometer instrument, could do. And then the dark black curve here is what we think we can do with the 40-kilometer instrument. And the curves that I'll show very quickly are simply just assuming different technology improvements. So this is kind of a slightly optimistic, this is a reasonable curve. This would be a curve we could design if we wanted the instrument to have wider bandwidth. Look how much wider it gets, but it's a little bit less sensitive. And then this is an instrument we would have if we were pessimistic. If we said the whole community is a bunch of fools, we don't know how to do any better on the technology, the only thing we can do is make it longer. Okay? So that's sort of what we're thinking of now. And here is the science reach that you could do. So these are those three curves that I showed, three possible curves. And what you should see here is this is redshift, and this is the maximum signal-to-noise ratio you could get for a pair of 30 solar mass black holes. And what you see is that pretty much out to a redshift, even with the most pessimistic curve, which is the yellow one, but the reasonable curve would be the red or the blue, you can see that you can get signal-to-noise ratio of tens, if not 100, out to a redshift of 10, and certainly out to a redshift of 20, it's still reasonable. So this is one of the reasons why we think Cosmic Explorer will be capable of mapping out the entire population of black holes in the universe, in these stellar mass black holes. Okay, so that's really the way to think about it. So I'm going to finish up. I'll just tell you, Lisa is really on a roll too. This is something fun to see about Lisa. In June this year, Lisa was selected by the European Space Agency with a thumbs up as a mission that they're going to fund. So Lisa is now back on track. And it follows a very successful test mission that was done for LISA called the LISA Pathfinder. And if you take away nothing from this sweet little curve, here's what you take away. This was the requirement, this light green curve, and this is what they've achieved. So they've actually achieved something like a factor of 10 or better than their requirement for LISA. And so it's looking very promising. So I'm just going to finish by saying, look, this is a field that has a really brilliantly dark and warped future. Okay, the current generations of instruments are really making detections at a good clip. If these rumors are true, it's even better than we think. Upgrades, as I showed you, are underway, and actually not just underway. I think we have some very good implementations being brought about. And we're studying the next generation of these tens of kilometer instruments, and it's looking like we can really do some amazing astrophysics with that. And then finally, Lisa is moving ahead too. So I'll end with this cartoon that I rather like. So if you think about only one message from my talk today, it's about sensitivity. We want to get more sensitive instruments so we can do more astrophysics. And so here is a rendition of The Princess and the Pea, where grandma says to the little girl, and thanks to this incredible sensitivity, they were able to use her to detect gravitational waves. Okay? And then there's the corollary that there's an added piece to it, which is grandma is really is thinking, really you want to have her in space for this sort of thing, but the detection apparatus is worse when it's dead. And grandma's thinking of Lisa, of course. But so I just want to say this is what we're doing at an exquisite scale. So stay tuned. I think this is a field that's just going to grow.
So we have time for a couple of questions.
So you mentioned the quantum noise associated with the vacuum for an empty port. I'm sure that you thought about it, but can you elaborate what happens if you play with that port and try to put some boundary conditions there? Is there a way of improving on that?
Yes. So that's a very good question. So in a quantum optical system, you can ask, what closes a port? And so what closes a port for the electromagnetic system is electromagnetic field. And so the open port brings in a vacuum field. You could imagine closing that off with some laser field, for example. And then what would happen is then you get into the trouble that laser does intrinsically bring its own noise.
Right.
And so then you actually screw yourself, because instead of having this rather low level of quantum vacuum noise, you have all the classical noise of the laser. So scratch that won't work. Then you can say, well, instead of a squeeze state, could you make some other exotic quantum state? And that's been looked at too, actually. And it turns out that there's a theoretical proof that shows that for this kind of measurement, and this is a very particular measurement where we're doing continuous measurement of order 10 to the 22 photons per second. So for this kind of measurement, the squeeze state is the idealized quantum state that you want to use. Now, you could ask, could you use other quantum states? Could you use number states, Fock states? Could you use noon states? These are all quantum optical states that people know how to make. And it turns out for these kinds of continuous wave measurements, none of those are good. Some for fundamental reasons and some for purely technological reasons. I'll give you an example. A noon state, actually on paper, you could say, yeah, that would look well. The best noon states we've made so far have 6 photons, as opposed to, so how can you compete with that in terms of the noise, reduction you get from 10 to the 22? So it's those kinds of
So you're
questions.
doing the best.
We think, but it's not perfect, right? Because you could ask, well, why are you only going for a square root of 2 improvement? What limits you to that? You can make a squeeze state, you just squeeze your ellipse narrower and narrower, and you do better and better. But it turns out that the reason you don't do that is that unfortunately in nature, and particularly in quantum mechanics, there is no free lunch. And so what this boils down to is optical losses. Anywhere in your system, if you have any optical loss, that's an open port. And so no matter how much we squeeze, eventually it doesn't matter because all these open ports are bringing in vacuum that replaces our squeeze state. So we're going about as good as we can do with current technology. But it's not our squeezers. Our squeezers regularly make factors of 4 or 5 in the squeezing ellipse. But you lose it as you deliver it to the interferometer because of losses. So.
Maybe time for one more quick question. Okay, now let's thank Nergis.
Thank you.
Okay, so today we're very happy to have Julian Munoz. Julian got his PhD at Johns Hopkins University, and now he's a postdoctoral fellow here at Harvard in the physics department with Professor Cora Dworkin. And he's been working on many things, CMB, dark matter inflation, and today he will talk about primordial black holes.
Thank you very much. Thank you for having me here. It's nice to be in the first center ever about black holes. I'm going to tell you about part of my work that intersects with this black hole, which is the idea of searching for primordial black holes. Let me start by saying this is work I've done with my advisor, Mark Mikowski, Professor Adam Rees, and postdocs Yasin, Simeon, Elias, Liang, Eli, and Albi Sim. So it's a part of, again, a large collaboration, not as large as LIGO, but this is not going to be, this is going to be much more from the theory side, and I hope you all learn something from this. So, let me start by asking just what are primordial black holes. We know that there are astrophysical black holes. We've seen plenty of them as X-ray binaries. They sort of form at the endpoint of stellar evolution. It's pretty interesting. But we're theorizing there could be a different sort of black hole, which are primordial. These black holes would be formed in the very early universe from overdensities in the plasma. When you have an overdensity that makes the gravitational potential much larger than the expansion rate, you would actually have the whole patch contract, form a black hole. This idea was first proposed by Soldovich in the 60s, and then explored by Stephen Hawking and Bernard Carr in the 70s. And if you actually, the good news of this is if you actually calculate what the mass of the black hole would be, is the mass contained inside the horizon. So to get black holes of hundreds of solar masses, these will be formed when the universe is around 1 millisecond old. So way before we have any observational constraints that could actually rule this out. Moreover, they give you a free dark matter candidate. You don't need to have any new particles beyond the standard model. You just have the regular standard model collapsing into a black hole. So this is plasma collapsed. However, here there's no free lunch either. And unfortunately, this also has some bad news, which is we don't know what would cause these overdensities. We need perturbations of order unity among patches. We need some patches to be twice as dense as the average. And we know from the CMB scales that the perturbations are of order 1 in 10 to the 5. So something fishy will have to go on in the very smallest scales.
And the temperature at that time is reachable in accelerators, so it's not, I mean, we know the physics at that time.
Right.
Except the QCD phase transition.
Yeah, they could be a QCD phase transition. I was actually talking about this before. And they could also, you don't know what the power spectrum, the initial power spectrum is. So you could have huge increase for whatever reason, huge peak in the delta square, okay? Because inflation is complicated, something could happen. But in some way you can think of this as, there's no such thing as a WIMP miracle for primordial black holes. There's no preferred scale at which you observe this, and there's no reason why it should be there, but it could. And the biggest problem, I'd say, is that there's a very fine-tuned process. So this time corresponds to redshift 10 to the 14. So if you form primordial black holes, they behave as matter, and they start redshifting slower than radiation. And eventually we know that matter dominates the universe at redshift 3000. So that means that you need roughly 1 out of 10 to the 11 patches to collapse to black holes, but the rest of them cannot, because you produce too much dark matter. So you need enough of them to make the dark matter, but not too many, since otherwise you overclose the universe. So it is clearly a complicated process, but I'm not too interested in how they form. I'm interested in trying to detect them, because if they are there, they are black holes, they come from the early universe, and it's a very interesting target. So how do we usually see black holes? Sometimes have regular astrophysical black holes, have companions, they accrete, you see X-ray, or gravitational waves. So how would you go around detecting primordial black holes if they make even a tiny fraction of the dark matter? But we can inspire ourselves on regular dark matter searches, where you have like a WIMP or some particle dark matter. You know that if these two dark matter particles interact, they can annihilate into standard model particles. This is what they usually refer to as indirect detection. And you can also have a standard model particle that is just here, and a dark matter particle hits it, scatters off it. There's the usual direct detection. So how this look like for primordial black holes? You know these black holes could in some way annihilate. They would form a binary and make gravitational waves, which are standard model particles we can detect. This would be the equivalent of indirect detection. And you know the standard model particles, like photons, get scattered near black holes. So just called gravitational lensing. So this would be the equivalent of direct detection. So I want to tell you how to use these two kind of processes to try to search for primordial black holes. And before I go any further, let me show you this slide. This is by recent paper by Bernard Carr, still working very actively on primordial black holes. And here he shows the fraction of dark matter allowed to be in the form of primordial black holes for different masses. You see the range is wild. It's from 10 to minus 17 solar masses to massive clusters of galaxies. There's different constraints all over the place from different processes. The reason why it stops here, by the way, is because any mass lower than this would have evaporated before today. So these would not be around anyway. You wouldn't see them. So again, before I get to the meat of my talk, this is a very solar exploration in different mass ranges, and it seems unlikely that the 100% of that matter could be made of these guys. I will keep referring to how much we can see of them as a fraction of the dark matter, since that is a much easier indication. But you see, at no point does this curve go to 1, as far as we can tell. But anyway, I'm going to be focusing on the range around tens of solar masses, which is this purple range over here. And the reason why, as we clear from the previous talk, is LIGO. LIGO has allowed us to see black holes with a mass range we hadn't seen before for the first time. So this is the first event. You all know everything about it, but briefly I want to say that the masses seem to be too high for what we knew at the time. Of course, this can be accommodated with astrophysical models. And if you take this 30-ish solar mass event, the rate from the first round of LIGO worked out to be around 0.6 to 12 events per gigaparsec cube per year. Of course, ever since we detected other events, there's another event that seems to be heavy. It's a 20 and 30 solar mass, which we heard about before. Whether you include or not in this kind of heavy black hole category is debatable, but we can take these rates as a fiducial. What LIGO detects of 30 solar mass-ish mergers. So, of course, if dark matter was made of primordial black holes, you would expect they couldn't make gravitational waves. So what we did is we worked out what the rate would be. So if you assume the dark matter is made of primordial black holes of 30 solar masses, there's a big if, but we're going to see where this if takes us. All the dark matter in the universe could be made of these guys, so clusters, the NFW halos that we know and love, we made of them. Every once in a while, two of these guys would come close to each other, and they could emit gravitational waves in a sort of Bremsstrahlung process. The energy emitted, we know is proportional to the quadruple square, triple derivative, G's and C's. So if you integrate this energy over a parabolic orbit, you get G, C's, and you get the mass of them to the 9 halves divided by the periastron distance to the 7 halves. You have to compare this with the initial energy they had, which energy at infinity is just the kinetic energy. So to form a binary, you need them to come close enough that they emit their kinetic energy. And by comparing this, you get a cross-section, which works out to be proportional to the Schwarzschild radius squared times this factor. Velocity over c to the minus 18/7. So the slower they go, the less energy they have to emit, the easier it is for them to form a binary. An interesting thing is the scale here is just the Schwarzschild radii. So it's actually have to come very close to each other. It's a pretty unlikely event. These are not the kind of binaries that would form in globular clusters, which are due to energy losses by 3-body interactions. These are 2-body processes. So, you can take this cross-section and integrate it over some halo when you have some number density of dark matter particles. Notice that because sigma depends on the Schwarzschild radius squared, the masses will cancel out. So whatever the mass you choose for your primordial black holes doesn't matter. And here we've chosen the NFW mass distribution, because that's what simulations seem to give us for cold dark matter. You could argue that these guys are not exactly cold dark matter, as they are black holes, they interact gravitationally. But we tried different profiles and this didn't seem to matter much. What matters, however, is what is the different velocity profiles of the halo. And to show that, here's a plot of the merger rate per halo as a function of the mass of the halo. So blue and green are different different results from simulations. And this black line is what you would get if you had a constant number of mergers per unit mass. And you see that lower mass halos, so these are very small halos. For reference, Milky Way halos 10 to the 12th or so. These small mass halos have more events than you would expect. And the reason is these halos have lower average velocities of their members. So this cross-section is largely enhanced. I also noticed that even on Milky Way size halos, the merger rate is less than 1 per Hubble time. So you wouldn't really expect this to be a common process. But if all dark matter is made of black holes, there's a lot of them. So you could the rate works out to be C. Yeah, I'll get back to that. Anyway, lower mass halos have more events. So when you integrate times some mass function, and you can choose different results for simulations, or even just analytically take the pressure sector mass function, you integrate from masses larger than some virial mass, you can see that you start going up and up as you go to lower masses. So you should cut off this at some point. And if you take seriously the possibility that dark matter is made of these 30 solar mass objects, there's a natural point at around 400 solar masses. If you have a cluster with less than around 15 objects, it would have evaporated before today. Or rather, if you start counting, they start evaporating once dark energy matter equality happens, or redshift 2 or 3, then by today, these halos would have just evaporated because the fast guys leave the halo. Again, this is an order of magnitude calculation, so you can cut off at 400 and you get a rate. And the rate you get is order 1 event per gigaparsec cube per year. And you really cannot do any better than order of magnitude here, because we don't know the smallest scale, how these halos work, where you should cut off. But you get order 1. Which, if you compare with the LIGO rate for the heavy events from the first run, it seems to overlap. It doesn't overlap with the whole rate, since we know we've seen more events with lighter masses like 50 and 20. But this could point that there's a population of primordial black holes that are detectable with LIGO. And the reason why we care about these tens of solar mass black holes now is because of this. These two numbers overlap. If you could have done this math, and you could have found that your orders of magnitude above this rate, and then you could very finely constrain with LIGO how much dark matter there is, you could be orders of magnitude below, and then you'll never see it. Be it as it may, this has prompted me and many other people to see what other ways are there to detect these black holes if they are there. And you might remember there's a lot of other pros. One of them is the CMB. So Jerry Ostreicher with Massimo Ricciotti and Katie Mack wrote a paper where they say that the CMB very much constrained dark matter fraction allowed to be in black holes. So these color lines are dynamic constraints, I'll get back to them. And these black lines are the constraints from the CMB. The physics here is you would have these black holes being dark matter, they're somewhere, they accrete baryons. These baryons from the accretion get heated up, emit X-rays, ionize the universe, heat up the universe. So because they heat it up, you get spectral distortions, which could be detected by FIRAS. And the anisotropies you would create are detected by WMAP. But more recent analysis have found numerical errors as well as wrong assumptions about the efficiency of the accretion, because they actually get super eddies and accretion at some part of the redshift range. And actually, no constraints can be get from spectral distortions, and only masses larger than about 100 solar masses can be detected with the most pessimistic assumptions about accretion. Which again, you could argue for hours about what the accretion should look like. Whether it should be spherical, maybe there's a disk. But with the most pessimistic, which is what you should do to get an upper limit, this cannot be detected with a CFD. So how else can we detect PDHs? Again, we look back to our WIMP analogy, where we talk about direct detection. So let's try to use gravitational lensing to observe these primordial black holes. So people have done this in the past, and the way this works in a cartoonish way is you have a star, let's say it's in the Large Magellanic Cloud, in our own galaxy, and if you have a primordial black hole or some compact object in the way, anything that is behind this Einstein radius of it is lensed. So the Einstein radius is roughly given by the square root of the mass times the distance. So if the star is behind it, it's lensed. However, you don't know what the intrinsic luminosity is of the star, so you cannot know if it's lensed or not to begin with. So you gotta wait for the star to move. And given that the black holes on the star are in the halo of the Milky Way or other galaxy, they have velocities of over 100 kilometers per second. So you can calculate the time scale for this thing to move. So for Einstein radius divided by velocity, works out to be 40 years for a 10 solar mass object. So over years, you see the stars that get brightened and then get back to normal luminosity. By looking for this kind of artificial variability, the Macho and Error survey have been able to put a constraint on the fraction of dark matter allowed to be in compact objects to be no larger than 10% of one solar mass, but this dies out around 30 solar masses. So before I go any further, let me say, this is not the full picture of what the constraints to primordial black holes are in this range. By now, there's many lines over many places, and I would say that to some certainty, we can say that no more than around 1 to 10% is allowed to be in this range. And what I'm going to tell you about is my own constraint to this mass range, which is obtained using gravitational lensing. It's clear that stars, like this kind of artificial variability, cannot take us all the way to higher masses. So what else can we use? What I propose is using fast radio bursts, or FRBs. And before I tell you what they are, when I'll do it in a minute, briefly the idea is you have an FRB, and this FRB is a very quick source, very thin. And then the two images, you actually see two different images with a different time of arrival. You cannot see it with the star, because the star is always emitting light. For an FRB, if it's thin enough, you would see a first image, and then an echo of it sometime later. And by looking for these echoes, we can look for primordial black holes. So, FRBs. What are FRBs? They're fast radio bursts. They're fast, they last like a millisecond or less, as far as we can tell. They are in the radio, have frequency of around 1 gigahertz, different spectra and different ranges, we don't know yet. And they are bursts of energy. We detect fluxes for 1 Jansky, which works out to be 10 to the 39 ergs at 1 gigaparsec. So its energy is much, much below a GRB, but orders of magnitude below. But still, it's an event we can see from far away. And we don't know what they are. As far as we can tell for now, there's more papers claiming they are different things than actual detections, but that is going to change soon. Anyway, this is one of the FRBs, 110220. It's like a bunch of noise, and then signal, and then more noise. And if you actually didn't know what they detect, all this signal is called a de-dispersed signal. The real signal comes over many frequency and time. So this, the yellow here means more signal, is where the signal is, and the rest is noise. See, the higher frequencies get to us before lower frequencies do for this FRB. And the reason is this FRB is radio, has to travel through a cold plasma. So there's free electrons, gives a plasma frequency, changes the speed of group velocity. So this time delay is related to a thing called the dispersion measure, which tells you how many free electrons there are on the line of sight. This is not a unique property of FRBs. Any radio source would actually show this kind of behavior. And in fact, you can look for pulsars emit in the radio, and if you plot where the pulsars are in the galactic plane versus the dispersion measure, you see the pulsars in the galactic plane have very high dispersion measure as there's a lot of electrons. But as you go up, there's less and less electrons, and the pulsars have very little dispersion measure. And here's the LMC and the SMC pulsars. If you plot FRBs in this fashion, you see they're all over the place. So we actually think they're extragalactic. And if you actually take this excess of dispersion measure for every pulsar, and you assume it's extragalactic, you can infer a redshift, assuming it just goes through average IGEA. It'll give you a rough estimate of what the redshift of the FRB is. I'll get back to that. But before that, if you go to the previous plot, remember each of the little dots over here is one little frequency bin, right? And the higher part of this frequency bin will arrive to us before the lower part. This is what creates this 1 millisecond width, which is comparable to whatever we can measure for the FRBs. So as far as we know, they last a millisecond or less. There's the scattering processes I'd be happy to talk about later, but roughly 1 millisecond is what we think the width of the FRBs is. So now, how would you detect lensing due to a primordial black hole or any of this? You have an FRB, you will be coming to Earth, and there's, you want to see two images, 1 and 2, you want to see them separated in time, and you want to see them bright enough. So first, you will require that the flux ratio of the first to the second image is smaller than some number. Because if you can detect the first and not the second, you cannot see lensing. This puts an upper bound on the impact parameter. Then you will require that the time delay between the first and the second image, which is a function of the impact parameter and the mass of the lens, is larger than 1 millisecond. The impact parameter, sorry, the 4 times m in units of time works out to be 1 millisecond for the 30 solar mass object, and this gives us a lower bound on the impact parameter. So in other words, all this means that for every primordial black hole, you have a range where if you're far away, you see two images, but the second one is too dim. If you're in this red ring, you see two well-separated bright FRBs. If you're too close, you only see one very bright burst that is white, so you cannot tell if it's 1 or 2. So now, for every FRB coming from some source redshift, ZS, you have to integrate along the line of sight, assuming all the dark matter is made of primordial black holes, and each of them has a little ring where you will cause lensing, and you can calculate the probability that an FRB is lensed. So as a function of the source that the FRB is coming from, if all your dark matter is made of 20 solar mass objects, you see that the FRB will have to come from very far away. So it intersects enough dark matter, and you actually can see this ring. As you increase the mass of the dark matter, this ring starts to fill up, since it's easier to create a 1 millisecond time delay. So then you start filling out this ring, and when you go to 300 solar masses or above, this is entirely a disk. So in any higher mass than this, you'll get the same result. Now, this is for an FRB coming from some redshift. As I said, we can infer roughly where the FRBs come from. And this is from the few FRBs we have detected, what is the inferred redshift you get from the dispersion measure. And they seem to come from cosmological distances from 0.2 to 1. In fact, for one of these guys, at least, we know that it's extragalactic because we have seen a counterpart. We have been able to, not a counterpart, we have actually seen this FRB repeating. And when we actually did the VLA observations, we could locate its host galaxy, which is at redshift 0.19 or so. So it's not that far off from the redshift you would infer. That's the point.
Well, what's the rep rate of these pulses that the FRBs are putting out? Like, how often do you get one?
Oh, every second in the year.
So they're millisecond wide, but repeating every second.
Every second, all the way to the edge of the observable universe. But the detectors we have right now detect roughly a few thousands per day. Can detect a few thousands per
A
day.
few thousand pulses per day.
Yeah, but they cover a small fraction of the sky, so they.
So I'm guessing how many there are. How many? Only one of them has been shown repeating, as far as I can tell, right?
Right, but she was asking how many are available for us to see.
Oh.
No, actually, I was asking really just what's the rep rate of.
One out of 20 seems to be repeating. That's as much as
And it repeats every week, every year, every.
we have not been able to observe it consistently enough, but as far as I can tell, there's repetition within minute timescales
Oh, okay.
and within years or at least hours. So
We've seen 200 repetitions of this
I think
one.
it's true. But like, there's like 100 here and then like 100 somewhere, right?
Right.
Okay, good.
I mean, they don't seem to be exactly periodic either, right?
No, not really.
So,
Okay.
but it's a good question. I'll get back to how that will contaminate the signal. Yeah.
Good.
I don't know if that was where
Yeah,
you were
that's
going.
where I was going, yeah.
Yeah. Okay, so cool. So this estimate we do is might be a little bit biased, but gives an estimate where these FRBs are coming from. And just so you have an order of magnitude, in the median here is around redshift 0.5. You take redshift 0.5 in the previous plot, you see the optical depth is around 0.01. So when you actually convolve these two functions, you get that the probability, which is optical depth roughly, is around 0.01 for a population of FRBs. So roughly 1 out of 100 FRBs should be lensed if they're cosmological. And this depends on the mass that you assume the dark matter is made of. So if all the dark matter is 20 solar mass objects, then it's very small, but it's like 50 or above, it's definitely more than 1%. So what does this mean? This means that if you detect a lot of FRBs, 1 out of 100 should be lensed. We've only seen 20, however. This is because we don't have telescopes that are covering all the sky all the time. The Parkes telescope or other similar ones have small field of views, and it just so happened that an FRB went off when we were looking. But time,
Let me ask you,
Yes.
what should be the distance apart on the sky of the two images?
Oh, tiny.
microsecond, I would say.
Yeah, micro.
But how do you tell that that's pretty small?
Time delay. Time delay.
There's only the time delay. So you can never actually resolve these.
I think so. Yeah, this is very, very small. I mean, yeah, you can do the estimate. For a galaxy, it's an arc-second, right? 10 to the 12 solar masses, so you go 10 to...
It is microsecond. That's why it's called microlensing.
Yeah.
Because of microsecond.
Okay.
So it's very small. But yeah, you would use the time information here. Cool. So, future experiments that are being built right now, Time, Hyrax, and Hera, will see tens of thousands of these guys per year. And the answer is related to what Avi was saying. There's a lot of them in the universe, and these guys will look half the sky each. So Time and Hyrax will have northern and southern hemispheres, I think, and Hera will have a band. So you have 10 to the 4, the number of lenses you expect, tau times NFRB, which try to be 10 to 100, if all the dark matter is made of 30 or larger solar mass objects.
And you infer the number in the universe just from the 20 that you've seen?
So here you don't have to really extrapolate that much. All you do is extrapolate to the rest of the sky. You don't have to assume a luminosity function of thing. What you say is, I look at this field of view, imagine I look for whatever many hours, and I see 1 every many hours per degree. If I had 20,000 degrees,
Okay.
you expect it. There's no extrapolation here about luminosity effect, or very, very mild effect. Yeah. So, if you didn't see any of these guys being echoed in this way, you'll be able to constrain how much dark matter there is for masses larger than around 20 solar masses, and the fraction you would see is less than 1%. You'll be able to constrain very precisely how many primordial black holes there are in the universe.
How many stellar mass black holes do we expect?
Good. Fewer. Because even just omega star is much more than, so like how many, yeah. Omega baryon is a fifth of dark matter, right?
Right.
Omega star is like, I think, like a 1% or so, right?
No, 10%.
10%, okay.
10%. So you're getting to the regime. If you have more FRBs, eventually you'll see the stellar mass ones.
Yeah, and I've been thinking about this, or whether you could see also substructure. If 1% of the dark matter is in, let's say, 10 to the 4, because this goes to infinity, really. This line keeps going. If you have 1% of the dark matter in the form of some clumps substructure, you could also see it with this. And if you had many more FRBs, it would be fantastic. But at the very least, we know that we'll be able to constrain this possibility. And related to the question that I was asked before is, what if these FRBs repeat? We know that one of them at least repeat, right? So what if, how do you tell whether it's lensing or natural repetition? And the answer is lensing creates a very strong correlation between the time delay of the images and the flux ratio of them. So if you fix where the lens is and where the source is, and you just change the impact parameter, you don't change the redshift, as you increase the impact parameter, you make the second image dimmer, so you move in this direction, and you also make the time delay longer, so you move in a line over here. Because neither the lens or the source are exactly fixed, there's this PDF, but if you see repetition from FRBs, you should put in this plot, and then if it follows this curve, it's lensing, but natural repetition, as far as we know so far, does not follow this curve at all. So, to sum up, I've been telling you how we've been searching for primordial black holes using LIGO, using gravitational waves. principle, this kind of tell you whether you're seeing stellar black holes or black holes, right? So because of this, I also looked at other probes such as lensing of FRBs. With this, you should not expect any signal right now from astrophysical black holes, but you might in the future if there's enough of them. But as I said, there's a lot of other work on trying to detect these tens of solar mass black holes from, for example, from the CMB I mentioned, from microlensing of distant quasars. So if you have a quasar that is microlensed, so it's strongly lensed by a galaxy, the different paths that go through the galaxy, and they go through different dark matter areas. If you have a lot of little lens masses, there will be artificial variability or microlensing. And by searching for this, they were able to put a constraint around 10%. And also from disrupted stellar systems. So if you had a stellar cluster that is in a dark matter cloud or some sort of cluster, these black holes would fly through, heat up the system, and you could disrupt it, or as Abby can probably tell you, you can change their radial profile. But be as it may, there's a lot of other constraints I'm not mentioning, and I'll be happy to discuss. But there's also different tools you can develop to look for these guys in gravitational waves, since, as I said, a black hole merger doesn't tell you whether these guys are primordial or not, but the spatial clustering of the gravitational wave signal should be different. If you get a lot of signals and they come from dark matter, they should be less clustered than if they come from baryons, from astrophysics. Also, these guys are from through this Bremsstrahlung-like process, so two-body interactions, so they seem to form very eccentric binaries. So you can look for this with LIGO. And I also want to point out that the idea of primordial black holes and gravitational waves is very old, and amongst the people working on this, Misao Sasaki is one of the most prominent, and he actually has a mechanism to form these binaries instead of this two-body Bremsstrahlung process through primordial binaries that form very early on and very slowly in spiral to merge today. So just wanted to point that out. So that's it. Thanks.
Nice talk. Is there any further question? Yeah.
Yeah, is there a unique prediction for the gravitational wave background of a
Yes.
bunch of these guys?
Ilias Solis actually worked that out. I'm not in that paper, but he worked out what the stochastic background would be. And
And it must put a limit then on.
you kind of limit it with LIGO, as far as I can tell. I don't remember, I think the result was by the very end of LIGO, because the stochastic background keeps decreasing with time, even if you don't improve the instrument. By the end of LIGO, even if you don't improve it, I think you might have a 1 sigma signal, but you really need to improve it. I think that's what the result was. But I think for most of these, for this two for sure, you basically need like what they call stage 3, like Einstein telescope light experiments, because there'll be a lot of astrophysical signal as well.
Okay, let's thank Julian again.
Yeah, so at 4:30 there's pizza with Colloquium speakers, although
Yeah.
I'm not sure, will you be here at 4:30 either? You have to rush off.
Not be able to today, but I'm here for a while longer now.
Okay, at 4:30 with Colloquium speaker, and if you have questions for Nergis, please get contact her.
So what keeps you from making a black holes like that? Just as a I get the idea that it's probably easy to do it with black holes.
Put out last year, who say he got
Only the idea that
black
black
holes.
holes is not the thing called dark matter.
As far as I can tell, who has confirmed that.
Yes, because you need dark matter to
Don't
exist.
really think it's in him.
I still have to
So that is what, yeah, so actually one of the things is we don't need dark matter at the end,
Sorry?
but we need